is 1, x2 is 3, x3 is minus 1. And you find a unique solution. And there was no other x values. In other words, there was no arbitrary part. Why?
The null space was 0? Or
This is the solution, but why we don't have the arbitrary part? Because in those cases, then we had a plus a to be a minus 1a, which is I. So I minus a plus a is 0. So automatically the arbitrary part was going away. And the solution is x is, it's a matrix solution, let's say x is a minus 1b, which is a unique solution because a minus a is s squared, is non-singular, so we have not the pseudo-inverse but the inverse, and then everything is cool. Remember, when we have a pseudo-inverse, we understand that this is not necessarily I. That is where the arbitrary part comes. That is where the arbitrary part comes. And it's actually I can easily write the unique solution is this. Why? Because the unique part is left, the arbitrary part is gone. So we had a theorem which called the existent theorem, which tells us under what condition we have a solution. And what was the condition, Dana?
a plus a to b.
A plus b is equal to b. In other words, Hassan, it means
Range of a is the subset.
subset of range of b that we had. Now, let's say a theorem which talks about uniqueness. So existence was telling us a plus b, I erase it, a plus b is equal to b, which means the range of b we have is a subset of the range of a. And now we want to talk about the theorem, which is called uniqueness theorem. And it says a solution of the matrix linear equation of ax is equal to b, where a belongs to R m by n and b belongs to R m by k, is unique if and only if we want to write something. I will fill the blank. But I continue. In other words, null space of A is equal to 0. Now, I want you to remember the two chapters that we had, one for fundamental subspaces and the other one for pseudo-inverse. What does it mean, null space of A equal to 0? From pseudo-inverse perspective. Or we can complete this one. It is a unique solution if and only if
The y part is 0.
The
Y part, like
arbitrary, it's got
Yeah.
arbitrary part is 0. Okay, very good. Let's write x was a plus b plus I minus a plus a y, right?
Mhm.
Y. So it's unique if the arbitrary part is 0. Now, one solution is y to be 0, which is out of question because y can be anything. So how can I have the arbitrary part to be 0? How can I have the arbitrary?
If A is non-singular.
How can I have the arbitrary part non-zero?
I was
It
going to
is
say
zero.
the same.
Hassan, how can I have this arbitrary part 0?
Either y equals to 0 or I minus a plus a equals to 0, which means I equals a plus a.
If and only if a plus a is equal to I. Which means n a equal to 0. So what was the meaning of n a equal to 0? We have a left inverse. We don't talk about singularity and anything. A plus a is equal to I. We understand that this means we don't know. If we have a left inverse, NA is equal to 0. If we have a left inverse, then it means NA is equal to 0. And if this is I, this part is 0. This part is 0. When it is I non-singular S4 matrix, automatically this is satisfied. Because then we have A inverse, which when this is an inverse, it's a left and right inverse. Let's do an example. Let's have an example. Suppose A belongs to R n by n. Find all solution of the homogeneous system Ax is equal to 0. What is the answer? Laura, what is the answer?
Like A is less than.
This is the general formula, right? What is B? Is 0. So X is,
Should be A plus B.
yeah, that's true. A plus 0, because it won't change anything in here. have a non-zero solution in here? Do I have a non-zero solution in here? Look. Do I have a non-zero solution?
Again, if there is a left inverse.
There is no left inverse. So there is a non-zero solution if and only if a plus a is not I. Because if it exists, this will be 0, so x will be 0. So in order not to have x to be 0, then a plus a should not be I. What does it mean? What does it mean a plus a is not I? Then it means that a is singular. Definitely a is singular, right? Because if a plus a is equal to I, then we have a potential of a not to be singular, it will be non-singular. In other words, rank of a is less than n. Rank of a is less than n, which means that there is a singular values, at least one singular value in a, which is 0. Because number of non-zero singular values is telling us what is the rank. And the rank is less than the size of our square matrix. In our book, the concept of reachability, controllability, observability, and reconstructability, which is basically the examples of 6.9 and 6.10 are mentioned. Read them for more information, but you are not responsible for them in the exam. Maybe Ike wants to read them because it can be useful for the control theory. But we are not responsible for this concept. There are definitions and terms like reachability, controllability, observability, and reconstructability.
This were included in the...
They are not included in the exam. They are not included in the homework. It's in the book, but you are not responsible for these two examples.
Okay, but these concepts were included in the course description.
They were included in the course description, but we don't talk about them. Because I want to talk about some other stuff. There are two examples, and in each example it talks about two of these things. If you have questions about them, you can ask, no problem. But you are not responsible for them in the exam. If you want, I can spend like about 30 minutes on them, but again, you will not be responsible. Maybe the best is that go over them. If you don't understand it, and if you want me to describe them, I will talk about them. But otherwise, I don't. So next session, which we have it on Wednesday, if you want me to describe them, you tell me at the beginning of the class, so I will spend about 30 minutes for them. But otherwise, I'm sure that you can figure it out by yourself. Even if I describe them in the class, you will not be responsible for that in the exam. Now, one more theorem. And the theorem says that let A belongs to R m by n, and B belongs to R m by q, and C belongs to R p by q. Then A x C is equal to B. Then the equation A x C is equal to B has a solution if and only if it has a solution if and only if A plus B, C plus C is equal to B. In which case, the general solution is x is A plus B C plus y minus A plus A y C plus. We can write it as A plus B C plus I minus A plus A, well, I mean, you cannot factorize it in an easy form. So keep it like that, and this is the arbitrary part. This is the unique part, and y belonging to R n by p is arbitrary. Now, which this means that we might need to revise a few very famous inverses or inverse of block matrices. But before that, let's see that if this is true for the previous situation that we had. The previous situation, we had Ax is equal to B, and we said the condition is that A plus B is equal to B. Now, if you want to write it, okay, you're right. Now, if you want to write it in the general form, it's actually AXI is equal to B, where we know that I is a non-singular square matrix. So the solution X, here X was A plus B plus Y minus A plus AY. Let's put it in here and see if the solution is okay. It's A plus B I plus Y minus A plus A Y I plus, which is A plus B plus Y minus A plus A Y. And the condition that we had, which is A plus A B I plus I is equal to B is A plus A, B is equal, sorry, A plus B is equal to B, because I plus I is I. Because I plus is I inverse, which is I. Which is I. Which means that this is a special case of here, where C is I, or C is 1, and this, we had a special case of AX equal to B for a non-singular S-square matrix of A, which we had it in undergraduate. Which we start by this point.
Turn it off.
Yep, please.